Welcome back, student. Now today we'll discuss about chemical equilibrium. Okay, already we discussed the fuel and combustion chapter, the theoretical air and excess air. The amount of air is required for the complete combustion. That is basically the greater than the theoretical air. That amount of air is basically called excess air. Okay, so we already discussed on theoretical and excess air. Now today we'll discuss about chemical equilibrium, which is very important in the context of for any type of chemical reaction when the fuel is react with the oxygen, which is basically when the fuel is oxidized or fuel is react with the oxygen and they will form some product with some energy. Okay, so obviously they will come into the text place that first law thermodynamics obviously we can apply. We already apply on this, and now we can apply the second law analysis for the chemical equilibrium conditions, for the reach actually for to maintain the chemical equilibrium conditions, which is very important because as you know that equilibrium is some state where the there is no entropy. Actually entropy comes zero in. Okay, so obviously from the second law thermodynamics, now when you the question will arise that how to find the direction of the chemical equilibrium. Okay, how to find the chemical equilibrium means how to find the direction of the chemical equilibrium in a particular combustion reaction. Now the answer will be that we have to invoke or we have to introduce the second law of thermodynamics so that we can so that we can actually derive, or we can say that the direction of the chemical reaction. Okay, so to find the direction of conversion of reactant to product, we can analyze or we can introduce the second law thermodynamics. Or from second law thermodynamics, as you know that Kelvin-Planck statement as well as Clausius statement. Now from this also we can give some another property, that is entropy, because from the first law thermodynamics you can get idea about the internal energy, and from the zeroth law thermodynamics we can get idea of the temperatures, as well as from the second law thermodynamics, which is very important for the chemical reaction purposes, that is entropy. Now from the second law thermodynamics, or we can get idea about the entropy, and we know that from that particular from the second law thermodynamics that ds system means change of entropy of the system, that is basically is greater than equals to dq by t. Now ds is equal to change of entropy, and dq is basically your the amount of heat transfer. Okay, amount of heat transfer, and T is the temperature. Okay, now so these are the general equations, or which indicate that ds system is greater than equals to dq by t, where if the ds system is equal to dq by t, then you can say that the process is basically reversible process. And if the delta S means ds system is greater than dq by t, is basically process is called basically irreversible process. Okay, now basically we already from the lower standard of the class we get some idea that the chemical reaction takes place in the proceeds means chemical reactions proceed in the direction of increasing entropy. Or you can say that entropy principle, from the concept of the entropy principle, that for a particular isolated system, and we can say that the entropy is only means chemical reaction are possible, or the entropy is always increasing, or it will be constant, but it will not be negative obviously. So the chemical reaction proceed in the direction of increasing entropy, otherwise not. If the entropy is change of entropy is increases, then we can say that actually that chemical reaction takes place. Okay, now we know that we assume that for the particular reversible process, or for the second of thermodynamics, if there is possible way that we can assume that there are two types of way, that is one is adiabatic process, if the chemical reaction takes place in adiabatically, or it may be that there is no adiabatic process at all, that means that reaction is follows the non-adiabatic process. But we can assume that for the ideal cases that it is a adiabatic process, but in actual and real cases that it is not adiabatic, it is not fully adiabatic, it is non-adiabatic process. Okay, now for the adiabatic process what happens, as you know that for the adiabatic process that change of heat transfer is equal to 0, that means dq is equal to 0, right? And you know that ds system is equal to greater than equals to dq by t. So for the adiabatic process dq is equal to 0, right? Now if you put these values here, dq is equal to 0, then you can get for the adiabatic process ds system is greater than 0, and you know that the chemical reaction proceeds in the direction of increasing entropy. Now for this conclusion, if the system is basically follows the adiabatic process, then if you draw the line is the entropy and equilibrium diagram, you can say that, or you can see that this is a diagram in which it can say that ds is greater than 0. So this line it reach with when the value is ds is equal to 0, and the downward direction graph it indicate that ds less than 0, which indicate actually violate the second law of thermodynamics. So in this area, actually in this zone, the chemical reaction doesn't take place. Okay, so particularly in this direction, chemical reaction takes place. So particularly in this point, because there is no reaction, just starting the reaction, so that means there's a 100% reactant. Here it will be 100% product. And you know that if ds system is ds is equal to 0, then it is, we can say that for the particular adiabatic process, if it is the adiabatic process, then we can only say that if ds is equal to 0, then we can say that the chemical reaction takes place, which is reaction takes place, that is basically equilibrium in condition. Now, if the question arises in your mind that if it is a non-adiabatic process, what happens? Now, if it is a non-adiabatic process, then two important thermodynamic potential function, that is Gibbs free energy equations, means Gibbs free or Gibbs function and Helmholtz functions, which is the basically two important functions, the Gibbs function or Gibbs free energy equations and the Helmholtz functions. Now, as you know that Gibbs energy or for the non-adiabatic process, G is equal to H minus Ts. I think all of you know that Gibbs free energy, that is G is equal to H minus Ts. So G is your Gibbs free energy and H minus Ts. Now if you differentiate this term, that will be dG is equal to dH minus TdS minus SdT. Now, and from the concept of enthalpy, that enthalpy is basically H is equal to U plus PV, right? H is equal to U plus PV. Now, if you differentiate, it will get dH is equal to du plus PdV plus VdP. Now, when you consider the equilibrium in condition, so obviously, if it is adiabatic or non-adiabatic, what happens? That it should be at constant pressure and constant temperatures. Now, if you apply in this equation, this condition actually is a constant pressure and constant temperature. Then, if it is at constant pressure and constant pressure, so this is the change of pressure V into dP term, and in this equation, dG is equal to SdT. So, at constant pressure and constant temperature, both term will be 0. So, ultimate equation becomes dG is equal to dH minus TdS and dH is equal to du plus PdV. Okay. Now, if you write this equation number 1 and number 2, and if you follow this number 1 and number 2 equation, you can get that dG is equal to dH minus TdS. Okay. So, from that equations, you can write down that dG is equal to dH in terms of du plus PdV here minus it is TdS. Okay. Now, you know that from the first law of thermodynamics, dq is equal to du plus dw. You know now, the dq is equal to du plus dw and dq is equal to du plus pdv. So in terms of du plus pdv, you can write here the dq. So dg will be written as from the first law of thermodynamics, that is dq minus tds. Okay, and from the second law of thermodynamics, you know that dg is equal to dq minus tds, which is basically less than equal to 0 at particular constant pressure and temperature. Obviously, the number of moles will be constant. So at a particular condition, the chemical equilibrium reaction takes place, otherwise not. So dG at particular temperature, pressure and number of moles will be constant. If its value is less than 0, less than equal to 0, then only the chemical reaction occurs. Now, when the chemical equilibrium takes place, there are two conditions. That condition is when the dG means change of Gibbs free energy equations or change of Gibbs free energy at particular constant pressure and temperature at particular number of moles is constant. If it is equal to 0, then it can only possible that the chemical equilibrium is reached. Okay. So if you look at this plot, what you see that these are G and equilibrium, that means the Gibbs free energy equation or Gibbs function, and this is the equilibrium. This is the diagram in which you can see that this is the Gibbs free energy equation. This is the dG is a change of Gibbs free energy, and this is also Gibbs free energy. And if the and it is only possible. So this is the condition for the chemical reaction if the Gibbs energy less than equals to 0. So if it is less than equals to 0, that chemical reaction takes place only this region. When it reach at dz equal to 0, that means it reach at the equilibrium condition. So if this particular condition is a 100% reactant, because there is no reaction takes place. Now when the total reaction occurs, there will be obviously 100% means reactant is converted into product. So at particular these conditions, that will be 100% product. So if it is dg less than 0, if it is dg is equal to 0, it will be dg greater than 0. That is basically violate the second law of thermodynamics. Okay, so that is the 100% product. Okay, so this is the feasible significance of chemical equilibrium in terms of first law of thermodynamics for an adiabatic process, for a non-adiabatic process. If you consider Gibbs free energy equation, Helmholtz equation, so all these equations if you consider, then you can get some idea for the particular chemical equilibrium condition for any type of chemical reaction. Now for a particular, if you consider as ideal gas, okay, so particular if any ideal gas are there, and if you get some mixture of ideal gases, then you can see that, or you can also written in this form that G mixture, okay, means Gibbs free energy, that mixture, that is equal to summation of I1 to N Ni GIT. Now what is Ni? Ni is your number of mixture, number of moles which is present in the Gibbs free energy on the reactant, okay, that is Ni into GIT. It indicates there are lots of reactant or product are there. So GIT indicates the Gibbs free energy for the ith species and at a particular constant temperature. Obviously at particular constant temperature. Now GIT, that indicates G suffix I comma T, that means the Gibbs free energy for the ith species at constant temperature, that is equal to GI, means Gibbs free energy for the ith species, that will be 1, 2, 3, 4 depending on the reactant and product, to the power means 0 comma T, that indicates at constant pressure, that means at 1 atmosphere, and 1 means at constant temperature, that means not constant temperature, standard temperature, that is 298 Kelvin, means at 1 atmosphere and 25 degrees Celsius or 298 Kelvin, plus RU, so that will be 2 here, that will be T, okay, RUT ln Pi by PO. So P0 P0, actually Pi by P0, that P0 basically the pressure, okay, it is a pressure, is basically chemical equilibrium pressure, okay. So and is equal to, if it is happens it is a GIT is equal to this one, so GIT in terms of that you can write here that I is equal to 1 to N. If it is I is equal to 1 to N, right, Ni into Gi dot. So this equation also written in this form here. Now we have to calculate what are the amount of mixture, means change of free energy equations, okay, for the ideal gases. So already we get that G mixture is equal to summation of Ni into Gi not T, that indicates basically the standard, okay, standard Gibbs free energy at particular ith species, that standard temperature, at standard temperature and standard pressure also, plus RUT ln P naught by, means Pi by P naught, which is basically a constant. P naught is a constant, that is a standard pressure, okay. So this is the G mixture. Now if you get differentiate that G mixture term, that will be DG mix is equal to D differentiate of this whole term, okay. So this term, now if you can differentiate, you can get that summation of DNI into this term, okay. If you differentiate this term, then what happens that if it is a constant, one time it will be constant and one time it will differentiate. So now just you only differentiate firstly, there is a two term Ni and G1, so if you differentiate only this term plus summation of Ni D of this term, okay. Now this is the differentiate term, so this is the differentiate equation, so this is the first term and this is the second term, okay. Now let's consider the second term. So this is the second term on a particular, after differentiating the equation, so this is the second term. Now when you differentiate this term, the equation that that summation of ni into d into gi naught comma t plus plus summation of ni into, so this term, so d of RUT, so RUT is basically also constant, okay. So summation of ni RUT is basically is constant, so summation of this one d of ln pi by p naught. So pi is basically the pressure for the ith space and p naught is your standard pressure, which is basically constant, okay. Now what happens that summation of ni RUT d of ln pi by p naught, if you get differentiate this term ln pi by p naught, you can get dp by dpi by pi, because p naught is the constant, okay. So you can write this equation also, RUT summation of ni into dpi by pi. dpi also, summation of dpi is the partial pressure for the ith spaces, because this is the summation of the total pressure is the summation of all the partial pressures. So summation of dpi is basically differentiate of all the partial pressures, that is basically 0. So if it is 0, then this equation become also 0, okay. So this, if it is this equation becomes 0, then this term also, second term also 0, okay. This second term also 0, and for the second term and it is the second term, okay. So this is the term, so this is the second term, in between second term this term basically 0, okay. So this term becomes 0, and for the particular standard condition the Gibbs free energy is also 0. So particularly this term is cancelled, because overall this term is 0, because of this term is 0 because of dpi by I, that d summation of dpi is equal to d of summation of pi, that is equal to 0. So that's why this term is 0. If this term is 0, so total term is 0, okay. Now remaining part, that is equal to summation of ni dgit at, that will be 0, because at a particular standard pressure and standard temperature for the ith species, that Gibbs energy is also 0. So if it is 0, then total second term of the differentiate the G mixer, that will be 0. So after differentiate only this term or first term is here, okay. So DG mixer, we can say that only this term. So that summation of dni gi naught t plus RUT ln pi by p0, which is basically at equilibrium condition. You know that for at equilibrium condition DG mixer it is equal to 0, and if it is DG mixer is less than 0, that means the chemical equilibrium takes place or the reaction takes place. And if the DG mixer, that means the change of Gibbs free energy of the mixer is equal to 0, then it can be possible that it can reach the chemical equilibrium. So for to reach the chemical equilibrium, it should be 0, okay, for 0, okay. Now let's consider the equation, that is AA plus BB is equal to CC plus DD, in which A, B, C and D are the stoichiometric coefficient on a particular. It is a random equation. Suppose CH4 plus O2 is equal to CO2 plus, it may be 2H2O, any kind of reaction takes place. Just we consider it arbitrary equations, that is AA plus BB plus CC plus DD, where small a, small b, small c and small d are the stoichiometric coefficient, okay, and capital AB, capital A, B, C, D are the reactant and also product correspondingly. Now, so after getting these equations, if you get, so we know that the ultimately to reach a particular mixer for the equilibrium, if it is reach the equilibrium condition, to reach your, if you calculate the GI naught or the Gibbs free energy for the ith species, we have to differentiate this term for the DG mixer for this particular equations. So if you differentiate this equation for the DG mixture, if it is a mixture of that, so it will be written as DNA. So that's why it's the ith species. So for the reactant A, that will be A here into G naught A, for the I will be A comma T, that is a plus RUT ln PA, that will be PI. For the here species is A, that's why PA by P0. Similarly for the B, that will be in DNB plus GB naught. Similarly that will be DNC. Similarly this one and this also DNB. So ultimately DG mixer equation, that also written in this form after differentiate, okay, because we know that DG mixer is equal to this term, because the second term is also 0. So ultimately equation becomes this one, DG mixer is equal to, so if you differentiate this term of the mixture, so you can get these equations. So by using law of mass actions, so you know that for the by using law of mass action is basically, so this one, your law of mass action, that is minus dNA by small a, which is stoichiometric coefficient, is equal to dNB minus of dNB by small b, that is your stoichiometric coefficient b. So that will be small c and small d, that is equal to k. Okay, if it is equal to k, then dNA is equal to minus a into k. So dNA, in terms of here dNA, so in terms of DNA from this equation, so you can write down dNA suffix a is equal to minus ak. So in terms of that, in the next line you can write is minus ak here, right? In terms of dNB, it also minus bk, you can write in the next line. And in terms of dNC, it can also written as ck, and dND also written as dk in terms of dND. Okay, so if you put this term, you can rewrite this equation like this. Okay. Now, as you know that for the mass of law of action, okay, law of mass actions. So dg mixture in terms of that minus dNA divided by small a, that is a stoichiometric constant, is equal to minus dNB by small b is equal to dNC by small c is equal to dND divided by small d is equal to k. Now, from that concept, you can, in terms of that minus dNA, you can write down minus ak, similarly for minus bk, similarly for ck and dk. So in terms of that, so if you write these equations on terms of this, so you can write this in this way. So that will be for the dg mixture for a particular equilibrium condition, that will be 0. Okay. So if it is 0, then you can get that c, that is basically c, that equation becomes c gc naught t naught, similarly d gd t naught minus agk is equal to delta g naught t, that is the means change of Gibbs free energy at particular constant temperature or constant pressure also, or standard pressure, standard temperature, that will be minus RUT. From this expression, if you calculate, then you can get that minus RUT ln PC by P0 is equal to PD by P0 divided by PA by P naught into PB by P naught, which is basically defined as Kp. So if it is defined as Kp, okay, if it is defined as a Kp, so this equation becomes actually this is indicated as Kp. Then from these equations we can write down that Kp is equal to, so Kp is equal to e to the power minus, if it is a summation of all these things equal to del g naught t, that equals to this one. So from this equation Kp is equal to e to the power minus del g t naught divided by RUT. Okay, so from this equation, so Kp you can get the value of Kp, or you can get the value of del g naught t naught. So del g t naught value, if it is positive, if it comes out positive, that means Kp less than 1, that means reactant are favorable. So that indicates that Kp, okay, so that's why Kp indicate the reactant are favorable in condition. Similarly, delta g t naught, if it is get negative value, that means Kp is greater than 1, okay, because delta g is greater than 1, so that means the products are favorable conditions. So in this way, actually we can say that it is a reactant favorable or product favorable conditions. Also, you can also calculate the Gibbs free energy during change or for the chemical equilibrium conditions. And one more thing, that that Kp is basically non-dimensional quantity. Okay, it's a non-dimensional quantity, and also it is only depend on temperature, not pressure. Okay, so these are the things that for the particular chemical equilibrium, what you taught actually, that chemical equilibrium basically, if it is a adiabatic process, then you can apply only second law thermodynamics. And if it is a non-adiabatic process, then we can introduce the Gibbs free energy, Helmholtz equations. Then we can get that DG mixture, means change of entropy, change of Gibbs free energy during mixture. Then if you get the random equations like AA plus BB plus CC plus DD, like methane also react with oxygen, they will form carbon dioxide and water. From that also you can also in terms of PC, PB and PA and PB, in terms of that you can, if you put all these things, then you can give value of Kp or del G T naught, which is basically your Gibbs free energy. Now if you know, depending on the value of this one, then you can say that is a product favorable, or it is a reactant favorable, or it is a chemical equilibrium, for if it is a chemical equilibrium in conditions. Okay, and Kp is basically non-dimensional quantity, and it is only dependent on temperature, not pressure. So Kp is a function of only T. Okay, thank you very much for listening and watching me, and goodbye.